morning, children. Let me start Chapter 1, Real Numbers, by reviewing the system of numbers. The extension of numbers from counting numbers or natural numbers to the system of irrational numbers. The system of counting numbers include 1, 2, 3, etc. We call them as the set of counting or natural numbers. By including 0 to these set of counting or natural numbers, the number system got extended to the set of whole numbers. With the inclusion of numbers below 0, the number system got extended to the set of integers. The numbers of the form p by q, where p and q are integers and q not equal to 0, are named as rational numbers. Any rational number can be expressed as a terminating decimal or a non-terminating recurring decimal. Recurring or repeating decimal. Numbers which are of the form non-terminating and non-recurring are called as irrational numbers. Thus, the real number system includes counting or natural numbers, whole numbers, integers, rational numbers, and irrational numbers. In this lesson, we are going to discuss about two important properties of positive integers. The first property of Euclids division lemma or algorithm. And the second property of the fundamental theorem of arithmetic. Let's go in detail. The first property of Euclid's division algorithm. Before discussion about algorithm, the word lemma, it is a proven statement which is helpful in proving the theorems. Euclid is the famous mathematician, or he is the father of geometry. As the word division is very clear to your mind, the lemma which connects with division is the property of dividend is equal to divisor into quotient plus remainder. This is the property we have used while checking the division problems. You will get the quotient and remainder by using this property of dividend is equal to divisor into quotient plus remainder. You can understand whether your division is perfect. The same logic is applied in Euclid's division lemma. Imagine the number 32 and the number 4. 32 is greater than 4. While division, We will take 32 as dividend and the divisor is 4. When you divide it, you are getting the remainder as 0. Try to increase the dividend by one number and the divisor being the same. You can see that the remainder turns to be 1. Let's divide 34 with 4. The remainder turns to be 2. 35 with 4, 8 4s are 32, remainder is 3. Let's increase 36, the divisor keeping the same, 9, 36, the remainder is becoming 0. Let's try with one more number, 37, 9 4s are 36, the remainder turns to be 1. In this way, if you continue, you can arrive at a conclusion that when the divisor is 4, the possible remainders you see for any dividend as 0, 1, 2 and 3. So let's define the general statement for the Euclid's division lemma in comparison with the example I have considered above or previously. Let a and b be two integers where a is greater than b. When you take a as the dividend and b as the divisor, there will be two another integers q and r which will be as quotient and remainder. Now, if you apply the general rule of dividend is equal to divisor into quotient plus remainder, the dividend we considered is a, divisor is b, the unique integers q as quotient and r as remainder, and the remainder will always lie between 0 and b. The remainder can always take the value of 0 or a number greater than 0. It cannot take the value of the divisor b. Thus, Euclid's division lemma states that let a and b, where a greater than b, be two integers, then there exist two unique integers q and r such that a is equal to bq plus r and r will always lie between 0 and the divisor. The remainder can possibly become 0 and greater than 0, but it should not be up to the divisor, or it cannot take the value of the divisor. So a is equal to bq plus r, where 0 less than or equal to r less than b. This is the general statement of Euclid's division lemma. How to apply this Euclid's division lemma as a step-by-step procedure for finding the HCF of 2 or 3 given numbers by division method. Exercise 1.1. Use Euclid's division algorithm to find the HCF of 135 and 225. The HCF of 135 and 225 by the application of Euclid's division algorithm. The word algorithm is related as a step-by-step procedure. So, considering 135 and 225, the bigger number 225 is considered as the dividend, the smaller number as the divisor. 135 is divisible one time. It goes as 90. Each step, please make sure that the remainder is smaller than the divisor. Now, 135 will be taken as the dividend. Division process continues. 90 is divisible one time. 45. Again, 45 is divisible by 2 times. You are getting the remainder as 0. So the long division has to be continued till you get the remainder as 0. Now, in the first step, now we are going to prepare the algorithm or the step-by-step procedure and finally getting the HCF of 135 and 225. In the first step, you can see 225 is taken as the dividend, divisor is 135, quotient is 1 and the remainder is 90. In this, that is, dividend is equal to divisor into quotient plus remainder. Second step, dividend is equal to divisor into quotient plus remainder. 135 is equal to divisor into quotient plus remainder. In the third step, dividend is equal to divisor into quotient plus remainder. 90 is equal to 45 into 2 plus 0. Thus, the HCF or greatest common divisor of 135 and 225 is the divisor which is in the last step or the divisor which is giving you the remainder 0. That is, the HCF is 45. So, the step-by-step procedure you are writing is called algorithm. This is the long division method. This is a possible 2 or 3 mark question in any CBSE exam. Question number 2. Find the HCF of 196 38,220 by Euclids division algorithm. 38,220 is the dividend, 196 is the divisor, the normal division as 1 time, even if the remainder 186 is here, you cannot proceed to the next step as the division is not complete with the first dividend. 196 multiplied by 9. The last step, the last digit as 0 comes down. 196 multiplied by 5. Thus, here only dividend 38,000 is equal to divisor into quotient plus remainder. Thus, the GCD, the greatest common divisor, or HCF of 196 and 38,220 is the number 196. The question number 3, 867 and 255, you can try on your own in the same method. Moving on to question number 2. Show that any positive odd integer is of the form 6 cube plus 1, 6 cube plus 3 or 6 cube plus 5 where q is some integer. Applying the condition of Euclids division lemma, let a and b be two integers such that A is equal to BQ plus R, where 0 less than or equal to R less than B. As in comparison with the question given, you can take the value of B as 6, and thus the possible value of the remainders are 0, 1, 2, 3, 4 and 5. By substituting the value of the remainders in the given, A is equal to, instead of B, 6Q plus 0 if the remainder is 0, which is equal to A is equal to 6Q. And how can you present that 6Q is an even number is any number divisible by 2 is considered as even. You can represent 6Q as 2 into 3Q, which shows that 6Q is a multiple of 2, or this number is an even number. If R takes the value 1, A is equal to 6Q plus 1. That means an even number plus 1 will always be an odd number. If R is equal to 2, A is equal to 6Q plus 2, an even number plus an even number will give you an even number. If R is equal to 3, A is equal to 6Q plus 3, which is again odd. If R is 4, A is equal to 6Q plus 4 is an even number. If R is equal to 5, A is equal to 6Q plus 5 is again odd. Thus, any odd integer, any positive odd integer is of the form 6Q plus 1, 6Q plus 3 and 6Q plus 5. The question also can be asked as, prove that any positive even integer is of the form 6Q, 6Q plus 2, 6Q plus 4. The same procedure follows. So in such questions, by comparing the given value, you can assume the value of B, and by getting the value of B, you can assume the value of the possible remainders. Substitute the value of the remainders in A is equal to BQ plus R and give a justification. Question number 4 can be taken as a similar way as we did as question number 2. So let's proceed with 4 and 5 first. Use Euclids division lemma to show that the square of any positive integer is either of the form 3m, 3m plus 1. Please underline the word square as well as underline the number 3, which will give you a clue to start with the question. As comparison with the Euclids division lemma, let A and B be two integers such that A is equal to BQ plus R, where 0 less than or equal to R less than B. 3m plus 1. By considering, you can take the value of B as 3. Once you get the value of B as 3, the possible remainders are 0, 1 and 2. If R is equal to 0, A is equal to 3Q plus 0, which is equal to 3Q. Here comes the word square. That means A square is equal to 3Q the whole square, which is the same as 9Q square, and they wanted you to express it as 3m or 3m plus 1. Take the common factor out as 3Q square. When you take the value of Q as any integer, 3Q square will be a number different from the value of Q. Let's call this as an integer m, where the m is taking the value as 3Q square. If R is equal to 1, A is equal to 3Q plus 1. a square is equal to 3q plus 1 the whole square. By the identity, a plus b the whole square is equal to a square plus 2ab plus b square. The expansion will be 9q square plus 6q plus 1. From these two, you can take the common factor as 3. It will be 3q square plus 2q plus 1. Call this as some other integer m. By taking the value of r as 2, if r is equal to 2, a is equal to 3q plus 2, a square is equal to 3q plus 2 the whole square, 9q square plus 2 into 2, 4 3s are 12q plus 4. Now, by seeing the question, you can see they are asking you to express it as 3m or 3m plus 1, whereas here the number you got it as 4. 9q square plus 12q plus 4 can be expressed as 3 plus 1. So from here you can take the common factor as 3q square, 4q plus 1, call this as m. Therefore, the square of any positive integer is of the form 3m plus 1. It's a very important question as a 3-mark or 2-mark question for the CBSE board. Passing on to question number 5. Use Euclids division lemma to show that the cube of any positive integer is either of the form 9m or 9m plus 1. When you see this question, underline the word cube and underline the number 9. When you see that, if you take the value of b as 9, the possible remainders are 0, 1, 2, 3, 4, 5, 6, 7, 8, and the workout with a plus b whole cube till the remainder 8 is too lengthy. In that case, since the values are given as 9m, 9m plus 1, 9m plus 8, you can take the value of b as any factor of 9. So the factor of 9 is 3. Let a and b be two integers such that a is equal to bq plus r, where you are assuming the value as of b as 3, that is a factor of 9, and the possible remainders are 0, 1 and 2. If r takes the value 0, a is equal to 3q plus 0, which is equal to 3q. You are asked to prove a cubed as 3q the whole cubed, which can be written as 27q cubed, or since you are asked to take out the factor 9 into 3q cubed as explained earlier, express this as the value of m. If r is equal to 1, a is equal to 3q plus 1, a cubed is equal to 3q plus 1 the whole cubed. Apply the identity a plus b the whole cubed as a cubed plus b cubed plus 3a square b plus 3ab square, which can be written as 27q cubed plus 3a square b, 3 into 9, 27q square into 1 plus 3ab square, 3 3s are 9q plus 1. Again 9m plus 1. So directly you can take it as, take 9 outside, 3q cube, 3q square plus q plus 1, call it as 9m plus 1. If r is equal to 2, a is equal to 3 cube plus 2, a cubed is equal to 3 cube plus 2 the whole cubed, which is equal to 27 cube plus 3 into 3 square is 9, 27 into 2, 54 q square plus 3ab square. 3 3s are 9, 9 4s are 36 q plus 8. Again 9m plus 8 is the form. You can take 9 outside, 3q cube plus 6q square plus 4q plus 8. Call it as m, which can be expressed as 9m plus 8. Therefore, cube of any positive integer can be expressed as 9m plus 9m, 9m plus 1, 9m plus 8. So, these are the possible pattern of questions which you can see in the first exercise.